We know that the power equation we had for the power available from wind for a wind turbine what had V for velocity in it. And velocity was the average wind speed. So now we're going to look at that equation again, and we're going to look at it for plugging in a distribution instead of an average wind speed. So we do need to, that involves calculus basically. Now, first, let's talk about what I mean by power density. So power density, I'm normalizing. So I want power over area. So I'm basically saying what is a power per swept area in meters squared. So I'm going to get watts per meter squared because I want to look at the power density instead of the power, because power is going to be higher if it's a bigger swept area. So a larger wind turbine has larger blades, it'll generate more power. But what I'm concerned with right now is not how big the wind turbine is. Of course, I'm going to get smaller power for smaller values of A, larger power for larger values of A, but I'm looking at the power per meter squared. So this is normalizing. This is like when you compare cereals. Well, there's an expensive cereal and there's a cheap cereal, but how much is each cereal per cup? So I'm normalizing, and I'm just choosing to do that so I can better compare the data. So taking out the effect of the wind turbine size, let's take a look at power density. So our power density then would be, we took our equation, which also had an A and a CP in it, and I divided by A to get power density. I'm also taking away CP because that's just a scale factor as well, and I don't care about the wind turbine's efficiency and everything. I'm caring about just what affects the power. So in general, I can generalize and call this power density. For the purposes of this lesson, which shows you the difference between the estimated and the correct power density. So here, the key part is that velocity V is average wind speed. So now let's look at the power density that is more correct. Well, average wind speed is not really of any use to us because wind speed actually varies in this Weibull distribution or Rayleigh distribution. So the correct power density would take that into account. So what it would be is it would still have the 1/2 rho velocity cubed, but then it would be multiplied by the probability distribution function as it relates to velocity. And you would need to integrate that between 0 and infinity. And when you're integrating that between 0 and infinity, this is what you're integrating times dV. Now, I don't need you to understand the calculus behind this. I just need you to recognize that we are now taking into effect the probability density function as it relates to velocity. Sorry, I was doing my velocities without a vector sign, which is hard for me to do. So this is the Weibull probability density function. And that's the previous equation. On the previous page, we have that equation. So if we now look at some average wind speeds that are 0 to 10, and we solve for the power density estimated and the correct power density, and again, the calculus of solving this is beyond the scope of this course, what you will see is that in the correct version that does take into account the probability density function, you can see that the power density is quite a lot higher here. And let's look at the next one. Quite a lot higher again, and a lot higher again, and a lot higher. So in conclusion, if we only use the average wind speed, then we are underestimating. So we are underestimating the wind speed by not using the power density function. So of course, a wind site would be chosen, and then the distribution would be calculated, and then you would know your parameters A and K, and then you would be able to calculate accurately the power density using that distribution with those values of K and A.